Okay, so now the ninth exercise. So this is a set theoretic identity we have to now prove. Two collections of sets are given. One of them consisting of the sets A alpha and the other consisting of the sets B beta, where the suffixes alpha and beta are labels which themselves are coming from two sets I and J. So for these two collections, we first take their unions and then we take the intersection of those two unions. We have to prove that this set is equal to the one on the right hand side. So it's a standard procedure. We have to prove that each one of these two sets is a subset of the other. Well, so we start off by showing that the left hand side is a subset of the right hand side. So let X be any element on the left hand side union B beta as beta varies over J. Then since this is intersection, so X will belong to both the sets. Now in each union, X has to belong to at least one set. That is, in this union, X has to belong to A alpha for at least one alpha in I, and similarly with this other union. This implies X belongs to A alpha for some alpha in I, and likewise from the other union we get this X belongs to B beta for some beta in J. Okay. Now what does it mean? Thus X belongs to A alpha and as well as B beta. So it belongs to their intersection. For some alpha belongs to I and beta belonging to J. Now this statement can also be written in terms of alpha comma beta, this ordered pair belonging to the Cartesian product of I and J. In other words, X belongs to A alpha intersection B beta for some such ordered pair belonging to this Cartesian product. Because you see, this part X alpha belonging to I and beta belonging to J is equivalent to this statement, alpha comma beta, the ordered pair belonging to the Cartesian product. So now what does it mean? We have shown that X belongs to one such set, one such intersection for at least one ordered pair belonging to I cross J. So that means X belongs to this union of such intersections. So X belongs to union of A alpha intersection B beta So one part of it is over. We have thus shown the following: union of A alpha intersection union of B beta is a subset of this set. Now we show the reverse inclusion. Now let Y belong to this set on the right hand side. Then Y belongs to at least one such intersection. For some alpha comma beta belonging to I cross J. This implies X belongs to A alpha intersection B beta for some. Basically here what we are doing is just the opposite of the steps what we have done here. For some alpha in I and beta in J, that is X belongs to A alpha for some alpha in I, and since X belongs to the intersection, it will belong to both the sets. X also belongs to B beta for some beta belonging to J. This further implies now since X belongs to at least one A alpha, so it will belong to the union of all the A alphas. Like that, X will also belong to the union of all the B betas. Or in other words, X belongs to both the unions, so it will belong to their intersection. Hence, this proves the reverse inclusion, that is, this union B beta is a subset of this intersection. And from these two inclusions, this one and this one, we have equality. And here the solution ends. The next exercise is about the graph of a function. I think in the last video I was saying that the ninth one is about the graph of a function. That was a mistake. The ninth one is about sets. The 10th one is about the graph of a function. But okay, let us just go through the exercise first, then we will discuss. If f from x to y is a function, so that means x and y are sets. Define the graph of f. To be the subset of x cross y, defined by like this. Show that if you think about it, you may find it somewhat strange if you are acutely observing the definition. We have defined the graph of the function to be a subset of x cross y. So for us the graph is actually a set, but looking at the word graph, naturally what happens is a picture comes in our mind, because we are familiar with graphs of functions as some diagrams that we draw on a graph paper. That is true when in place of x and y we have the set of real numbers. Then we can think of r cross r as the two-dimensional Cartesian plane with the Cartesian coordinate system. There we identify this set with a figure actually. The real definition of graph is this, as a subset of x cross y without any reference to geometry. However, in that particular case we can actually draw some diagram, but you can see here x and y can be any sets. So if you really think about it, in a general situation where x and y don't necessarily have real numbers, you cannot draw anything, but this set exists nevertheless, and this is defined to be the graph of f. In this special case we can draw, and that aids to our understanding of the situation even more. Just by looking at the whole figure you can know many things about the function at once. So the general graph is a set, or rather a subset of x cross y defined like this. Okay, so now what do we have to show? Show that two functions one of them is f and the other is f tilde from x to y are equal if and only if they have the same graph. Okay, so a function is characterized by its graph. Conversely, so this is when two functions are, if functions are given, then their graphs can be drawn, and using them we can identify functions, whether they are the same function or different function or not. Conversely, but if a set that behaves like a graph is given, what do we mean by that? Conversely, if G is a subset of x cross y, where x and y are some sets that are already given to us. If G is a subset of x cross y with the property that for every x in x, yes, for each x belonging to x, the set x comma y, the set of ordered pairs where the first coordinate is x and the second coordinate can be anything. So the second coordinate is coming from y, that much we know. Don't know anything about it, anything else about it. And this set has exactly one element. Now wait, oh no, I have written the wrong set, not this set, sorry about that. The set of all elements in Y such that the ordered pair x comma y belongs to, it has to somehow be linked with G, such that the ordered pair belongs to G has exactly one element. Or in other words, G obeys the vertical line test. Show that there is exactly one function, yes. With domain x and range y, whose graph is G. Okay, now I must mention at this point something about this word graph, other than the fact that in a general case we cannot draw graphs, they are just subsets. The name graph by itself means something else in mathematics. Those of you who are familiar with graphs from graph theory, they know that graphs consist of some vertices and maybe some edges between them. So that is something different. This is this concept is associated to a function. Okay, this concept is not necessarily associated to any function. A graph by itself is we will discuss about it at some point, is an object by itself, not necessarily associated with any function. Okay, so one more thing that we must make clear is what is this vertical line test. You see, what we are doing here with G is a subset of x cross y that is supposed to satisfy some property that looks like this, and we are calling that property the vertical line test. Let us see what this all means in our familiar case where x and y are the set of real numbers. Suppose we have this situation. X and y are both the set of real numbers, so that we are dealing with a real valued function of a real variable, the ordinary type of functions that we come across. Then we can draw a graph of that function, however the graph may be. However, in this converse part, we are already given a graph, we are already given a figure, and that figure is supposed to satisfy this condition which we are calling the vertical line test. Let us actually consider a figure. Suppose my G in this special case is this. It is the set of all x comma y belonging to, you see, G has to be a subset of x cross y. For us, x and y are R. So this is just R cross R, which sometimes is also written as R2, such that x square plus y square is equal to 1. You already know what this is. This is the unit circle centered at the origin. Okay, I may not be able to draw it properly, but you can understand. The unit circle centered at the origin. Center is at the origin and it has radius 1. Right. Now, what this one says, for each x belonging to x, our x is again the set of real numbers. For each x belonging to x, well, for this case, this will not exactly say what is written here. Let us take a restricted x and y. We are taking x and y to be both this closed interval -1, 1. Then here, instead of r square, we will have -1, 1 r2, sorry, -1, 1, 2. That is -1, 1 cross -1, 1. So now our set x cross y is not the entire plane, but rather this square, whose coordinates of whose vertices are 1, 1, 1 minus 1, -1, 1 and -1, -1. Okay. Now x is -1, 1 for each x belonging to x. That means x varies horizontally, y is varying vertically. So if I take any point, say my x is here, which is some point, which is some negative value of x equal to 0 sits here. For that, if I draw a vertical line passing through this point, what do the points on this vertical line look like? I mean, what what will their coordinates be? For specificity, let us take x naught. The points on this line will look like x naught comma y, where y can take its value between -1 and 1, because y is also coming from y. So my point can be anywhere on this vertical line. Okay, so now if my x coordinate of this point is x naught and y coordinate is any y from y, how many of such points lie on G? What is my G now? This is my G, this circle, unit circle. There are exactly 2 points, this one and this one. There are values of y, say x naught comma y1 and x naught comma y2, 2 values of y for which the points lie in this G. Accordingly, there are 2 values of y. So that means if I form this set for in this special situation, the set does not have exactly 1 element, it has 2 elements. That is, this set for us will be y1 comma y2. So this G fails the vertical line test. The vertical line test says that if you draw any vertical line, I mean in this particular case, because we are deriving this definition from this particular case, so that's why the terminologies are like that. Vertical line, they are coming from geometry. If that line crosses the graph or crosses the figure at not at exactly 2 points, then the figure is not the graph of any function, and indeed this is not the graph of any function, because here for a given x you are getting 2 values of y. So the property that functions have, that for a given input there should be exactly 1 output, that property is not satisfied. So that's why that cannot be the graph of any function like this one. For a figure to be a graph of a function, for every x, for every input, there should be exactly 1 output such that their ordered pair belongs to that figure, such as this one. Just giving one example, y is equal to x square, the parabolic graph. Here if you draw, this goes on and on, okay, without bounds, excuse me. If you draw any vertical line, that for any x there is exactly 1 y for which x comma y belongs to the figure G. Here I am saying figure because we can draw. In the general case we will say set. So that is the vertical line test, and that's why it is called the vertical line test. Okay, let us now go to the solution. So that's why y is equal to x square actually is a function, or that figure is the graph of a function. Anyway, so now in the solution what we have to do first is prove that 2 functions are equal if and only if their graphs are equal. From the definition of the graph of a function, it's clear that the graphs of 2 equal functions are equal. It's almost obvious, so obvious that we are not writing anything more than this. That's because if you take, say, you have these two functions where they are equal, that means they have the same domain, same range, and they also do the same thing to an output. That is, fx is equal to f tilde x for all x belonging to x. Then clearly this set that you will form for f and f tilde, they will also be equal, identical. So that's why the graphs are the same. Now conversely, if they have the same graph, conversely let f from x1 to y1 and f tilde from x2 to y2 be two functions having the same graph. Note that the only hypothesis we are making is that they have the same graph. We have no right to assume that they have the same domain or same range before proving anything. That is, those things we have to show from this hypothesis that they have the same graph. X comma f of x as x belongs to x1 is equal. I won't have space. Instead, I write this one properly and write the next set there. Oh no, see, we need not take separate domains and range because the exercise itself assumes that they have the same domain and range. Okay, so we have x and y. So I thought something else. So we just have to prove that they are doing the same thing to every input. Be two functions having the same graph. That is, this is equal to x comma f tilde x, where x varies over x. We have to now prove that fx is equal to f tilde x for every x in x. So let x belonging to x be any element then fx, okay, so if x belongs to x is any element, then x comma fx, this belongs to the graph of the first function, graph of f. But we know that this set is equal to that set. Hence, x comma fx belongs to the other set also. Which implies that this ordered pair will be equal to some other ordered pair for some x prime belonging to x, some other ordered pair belonging to the second set. But then, because these two ordered pairs are equal, so corresponding coordinates should be equal. X is equal to x prime and fx is equal to f tilde x prime, and hence using this here we get fx is equal to f tilde x. So the functions f and f tilde, besides having the same domain and same range, also have identical outputs, thus they are equal. F is equal to f tilde. So two such functions are equal if and only if their graphs are equal. Now we have to prove that if a subset G of x cross y is given to us that satisfies the vertical line test, then there exists exactly one function whose graph is G. Okay, so next let G be a subset of x cross y, and this satisfy the vertical line test. Sometimes such a name which does not have any mathematical symbol is easier to refer to.